All right, so we are asked to simplify this expression. I didn't write down the instructions, but I'll tell them to you. We want to simplify. You see that you're composing tangent with arctangent. So you know this is going to be whatever the inside argument is, as long as 7 is in the domain of the inside function. And the domain of arctangent is everything. So of course 7 is in there. And so this just composes to 7. Done. How nice. Next one, we want to simplify the cosine of the inverse tangent of x. And so this is just like the previous simplification problem that we did. The difference is instead of a number, I have a variable there, but whatever, we can handle it. So same strategy, we're going to let theta equals inverse tangent of x. So that means that, let's actually use letters. So we'll say, so tangent theta equals x. And now from this, once you've translated your inverse trig function in terms of the trig function, tangent, you can always draw an associated triangle. So this triangle I'm going to draw, I'm going to think about this as theta. Tangent of theta is opposite over adjacent, and that's x. So I can write this as x over 1. That gives me x. And that allows me to easily fill in this side, square root of 1 squared plus x squared. So now I'm ready to go. So when I'm interested in the cosine of the inverse tangent of x, well, we said that inverse tangent of x was theta. So this is exactly the same thing as the cosine of theta. And the cosine of theta, looking here now, is adjacent over hypotenuse. And so cosine of theta is 1 over the square root of 1 plus x squared. And so that is what this thing actually simplifies down to. All right, next, I want to do a limit example with you. We want to take the limit as x goes to infinity of this function. Now, you could probably just reason through this and write the answer down, but I want to show you how you can actually communicate your work. So let's reason together for just a minute. So we can say as x goes to infinity, I want you to think about what the inside does. Well, you know, as x goes to infinity, x squared goes to infinity. As x squared goes to infinity, e to the x squared goes to infinity. And so, of course, adding 1 just makes you ever so slightly bigger. And so the point is, as x goes to infinity, e to the x squared plus 1 is also going to infinity. So here's what you can do. What's nice is if you call u e to the x squared plus 1, maybe instead of call, I should just say let. Let's say let u be e to the x squared plus 1. And so the point is u goes to infinity as x goes to infinity. We just said that. And so this allows you to rewrite your limit in the following way. The limit as x goes to infinity of the arctangent of e to the x squared plus 1 is equal to the limit. Now think with me, what's happening? X is going to infinity, pushes this to infinity. But we called this u. And so I can write this as the limit as u goes to infinity of the arctangent of u. And I know that that's just pi halves. We know that as the inside of arctangent goes to infinity, the whole thing goes to pi halves. So this is just a way you can write it. You could have reasoned through it and said, look, as x gets big, this gets big, so this gets big, so this gets big, and as this gets really big, this thing is going to pi halves. That's fine. If you can see that, you're like 95% there. That's excellent. How do you write that down? Well, you can give a name, call the inside argument another variable, and then you can notice its behavior and then rewrite your limit like I did right here. That's how you can actually show it. Don't let that cause you too much angst, but that is how you can write it down. Okay, fourth example. Let's take a quick derivative and make sure that we're good to go on this. So f prime of x in this case, I'm going to have to do the product rule. So the derivative of x, we know is 1, times inverse tangent of x squared plus 1, plus x times the derivative of this guy. All right, how do we do that? Well, it's going to be 1 over 1 plus, actually, let's pause. The derivative of just arctangent of x in general is 1 over 1 plus x squared. I've got to plug the inside into this x squared. So I get 1 over x squared plus 1 squared times the derivative of the inside, which is 2x. And so in the end here, when I clean this up, I get that f prime of x is the arctangent of x squared plus 1 plus a 2x squared. And you have to choose, do you want to factor the bottom here out or not? I'll factor it out, sure. I get x to the fourth plus 2x squared plus 1 plus 1 is 2. And so this is what you get when you want to work out f prime. All right, last example. How do you evaluate the arc cosine of square root of 2 over 2? You'll see some of these on your homework. Call this C. And then you know arc cosine sends root 2 over 2 to C if and only if the cosine of C equals root 2 over 2. And now you think about your unit circle. What do I plug into cosine to get root 2 over 2? And by the way, think about it with me. C is in the range of arc cosine. The range of arc cosine is the domain of cosine is 0 to pi. So you're looking for a C that needs to be between 0 and less than pi, less than or equal to pi, between 0 and pi. Because there's actually infinitely many angles you can plug in here to get out root 2 over 2, but there's only one that's between 0 and pi, and the one is, of course, pi fourths. So C is pi fourths. And so that tells you that the inverse cosine of square root of 2 over 2 is exactly pi fourths. All right, well, you should have what you need to do the homework. Before we go, though, I want to do one more video, and I'm going to show you a handout that I made. So you can just find the handout on Teams, but I'll actually show it to you here in video form as well. Super short video for the last one.